Before we get into our last topic in this section, we want to take a minute and review how to find normal vectors in a two-dimensional real number system. This only works in 2 dimensions, the particular way that we've learned how to do this. In 3 dimensions, all bets are off and you have to do more elaborate work. But 2 dimensions is relatively easy to find normal vectors. All right, so we have this curve, y equals x squared. Now, to parameterize that, there's infinitely many ways to do that. We learned that in Calc 2 or in pre-calc when we first learned how to do parametric functions. The easiest way to do it, and the way we tend to use most often, is to let your x be t, and therefore your y would be whatever your function was, in this case t squared. And you'd have to have some type of domain usually, but we don't need that particular one, right? Because we're not going any further with this, but you'd have a domain. All right, so now I actually want to look at this point over here, which is at 1, 1. So I want to look at everything at t equals 1. Okay, so at t equals 1, r of 1 would be 1, 1, which is that point. Technically, it's in parametric form, so it's a vector, or excuse me, in vector form. So it's a vector from 0, 0 to 1, 1, but you know, it's not worth our time to draw the arrows. Right? If you want, you can put it in there. All right, now I want to look at the tangent vector. So the tangent vector, right, this is the tangent vector, is at t. And we're not really doing a unit tangent vector, so let me just make this a tau or something like that, because it's not the unit tangent. Capital T is kind of specific. So this is 1 to t, right? It's r prime. Right? And so at 1, right, r prime at 1, or if you will, tau at 1, tau being my tangent, would be 1, 2. All right, so let's think about that for a second. So we have this point right here, and so we'd be going over 1 up 2. So it's going to shoot this direction, right? That's tau. Right? This is the tangent. It's the direction of motion. All right, now what about the normal vector? Well, the normal vector, this is kind of the key we want to make, is that there's actually 2 ways to do this. So there's one normal vector, which I'm going to do right here, and that would be to take the tangent vector, to take the 2 components of the tangent vector, and to reverse them. So you say, okay, 2t and then -1. Right? You take the tangent vector and you flip them. Right? So let me make a note. You flip the tangent vector and make 1 negative. So in this case, we made the back negative. But there's another way as well. So the normal could also be flip them, but make the front the -1. That would also work, right? Now, is there a difference between these 2? Yes, and let me show you what it's going to be. So if you want to see the normal vector, this particular one, at 1, that would be 2, -1. All right, so let's think about what that would look like. So here you are at this point. You're going to go over 2 down -1, which means you're going that direction. So you're pointing out against the curve. I didn't like the way I drew that. I'm trying to draw it so it makes a 90-degree angle so you can see it better. All right, so this is the normal vector, but this is pointing out. It's pointing away, right, outside. So there's a concavity to this curve, and we're pointing out to the outside of that curve. So that's what this one is. This one's the out one. When you make the back number negative, it makes it out. As opposed to this particular one, if I look at this one, this would be the n at 1 would be -2, +1, which is going in the exact opposite way. It's going like this. So this is the inner one, and this is the outer one. Right? This one's pointing in towards the concavity, or convexity if you want to think of it that way, and this one's pointing outward. Okay, so this is the inner, right, inside one, and this is the outside one. Back when we first learned how to do this in the first chapter of the course, it didn't really matter which one you did, right? For our purposes, we will tend to stick with the outer one. That's just standard. So this is the one that we tend to work with. The other one is also there. It just tends not to be the one that we're using for this particular application that we're about to do. So let's start this. So we're interested in the outward flux, as a matter of fact. So that's what we want to look at. Okay, so we saw what happened when we took the line integral with the vector field times t, where t was the tangent vector, but n is a normal vector. Right. Now, what's this going to give us? This is going to give us the amount that the vector field pushes outward in the normal direction. Right, so it's how much is pushing through, how much of this vector field is pushing through in the outward direction. That's why we care about the outward normal vector. That's the one that we're going to use a lot, right? So it's how much is it pushing outward, and that's called flux. It's how much the vector field is permeating or pushing out. All right, so let's look at a couple points on this and kind of get a sense of the flux. So we see we have this curve right here, if you can see it. It's right there. There's a curve going around. All right, so we have a circulation to this curve. So we're going this way, and then we're going this way. And then, oh, it looks like we're going this way for this piece. So there's two pieces. So it's saying on curve 1, which is, let's see, curve 1. Oh, I see. This is curve 1 right here. So on curve 1, which is this piece, right, how much flux do we have? Well, you can see it's the arrows are pushing out, right? They're pushing out across that curve. So on curve 1, which is right here, C1, that's that curve, the flux, which is capital Phi, by the way, is positive. And then I know that called these curve 2, but I'm actually going to separate them. So I'm going to make this curve 2 and this curve 3. So on curve 2, right, it's this way, and you can see it's pushing inward. See, the arrows are pushing in. That means that your flux would be negative on curve 2. And then curve 3 is right here. And again, those arrows, that vector field's pushing across that barrier, across that curve, inward. So since it's pushing inward, the flux would be negative. Now we're going to look at the integral, but in 2 dimensions only, and that's because we can come up with the normal curve really easily in 2 dimensions. So that's why we're doing that. All right, so how is this integral f dot n ds evaluated? So n is the outward pointing unit normal vector. Since n must be perpendicular to t, so let's think about this. T would be r prime divided by the magnitude of r prime. And so that would be dx dt dy dt over the square root. Well, I'm just going to say r prime. You know what it would be. All right, we don't have to worry about that part. Okay, so how does the normal vector change? So the normal vector is, since we want the outward one, we want to take dy dt in the front and then negative dx dt in the back. And we would divide it by the magnitude of r prime. And remember that we have ds. We already know ds. ds is the magnitude of r prime dt. We already ran into that. And so putting this together, if I want the line integral of f dot n ds, then what I really want is the line integral over the curve. Well, I'll just say from a to b. Let's do it that way. And then f. And then for n, we would have this piece, right? It would be dy dt negative dx dt over the magnitude of r prime. And then we would multiply it by ds, which is the magnitude of r prime dt. Well, obviously the magnitude of r primes are going to go away, and that leads us to the integral from a to b of f, the vector field, times dy dt comma negative dx dt. And again, that negative is in the back to get you the outward. I should have mentioned that, right? Technically, there is another inward flux, but we don't do it that way. So flux, they had to pick a direction back in the day, and they picked the direction they went with. All right, so dt, and this is equal to the integral from a to b of f dot n dt, where n is equal to, and again, this only works for two dimensions, dy dt negative dx dt. 3 dimensions is much, much tougher. And don't worry about this. I don't know why that's there. That's a typo. So we're good. And this gives us the formulas for flux. So you can see flux is written this way right here. And in 2 dimensions and in 3 dimensions, it's this way as well. It's just that in 3 dimensions, finding that normal vector is hard to do. Right? In 2D, n is this. Oh, I should also mention real quick before we go, I think this is where actually I was going with this piece down here, which is that there's an alternative form. If I take this same integral, I can also write it, the integral from a to b. If you think about what this would be, the dt's could cancel. It would be f dy, right? So if if vector field f is f times g, I take it back, this was not a typo. One second. There, that's all we need. So if we took the dot product, f comma g, dot product with dy dt negative dx dt, it'll become f dy minus g dx. That's an alternative form. So we have 3 forms here, right? Right here, right here, and right here. We use the middle form a lot, but the problem is you can only use the middle form if you know that normal vector. So that means we're also going to be using this alternative form a lot. And we'll see how to do that in some examples later. Suffice to say, it's not going to be easy in this particular, in 2 dimensions it's fine. In 3 dimensions it'll get a little bit more difficult.